welcome to our second speaker, and we have at least one lightning talk afterwards. Yes, great. So yeah, please welcome Florian. He's going to talk about Kartothek, and yeah, and thank you. Introduce yourself. Yeah, okay.
Thanks. Yeah, hello everyone. I want to introduce Kartothek, which is a Python library for Parquet table management we built. What this exactly means will hopefully become clear in a few minutes. But for starters, my name is Florian. I'm working at Blue Yonder as a data scientist / data engineer, and I'm primarily working towards setting up our architecture to use these Parquet tables. To get started, I want to quickly tell you what our company is actually about, to get you a feeling about what kind of data we manage. So JDA is our parent company. JDA acquired us mid last year, and essentially they have a very broad portfolio ranging from everything related to logistics, warehouse management, and so on. We at Blue Yonder manage only a small section of this, namely demand forecast, pricing optimization, procure optimization, and so on. So what we do is we get our customer data, like something like, think of sales data, stocks data per location, per product, prices, procurement information, something like when can the store order what amount, something like this. And we perform machine learning to make a demand forecast, and in the end perform optimizations such that there is no waste, no out of stock situation, and so on and so forth. So what that means in numbers, so I divided this into two sections to give you a feeling about what our data size is. So we get our data submitted by the customer. We refer to this as our core data, and you can think about a mid to large or mid-sized retailer think of 1,000 locations, physical locations where you have about 20 to 30,000 products or SKUs. That makes up about 25 million data points we have per day. So what we do is we perform time series forecasts for 25 million time series every day. If we talk about Parquet and in-memory data size, in Parquet file, this is actually only about 1 gigabyte, but this is only because there is very nice compression algorithms and encodings, as Uwe mentioned before. We usually store 2 to 6 years of data, so overall that makes up a few terabytes of data per customer we have. But this is only one side of things, because this is the core data, this is our input, so to say. And what are we doing? We are doing machine learning, so we generate a lot of data garbage. So what we do is we generate about 1 billion rows per day when we do our forecasts, our orders, and so on and so forth, which amounts to about, in a pandas memory data frame, it's about half a terabyte of RAM. This is about the data scale we are talking about, and this is essentially running in production every single day. So data engineering, both efficient, cheap, and easy, is, so to say, a very important thing for us. To motivate a little bit about what got us started to build an alternative storage technology, think of a typical ETL pipeline. You start with a relational database. You extract some data, you load it, you perform joins, which are usually quite expensive, but in the end, your machine learning application needs flat data, because that's just the way it is. Then we process the stuff. We usually use some compute cluster. In our case, it's Dask, which is why I will talk a little bit about Dask later on, but think of something else like Spark or something similar. That where you have 100 or a few hundred of hundreds workers running on a cluster manager, and in the end they produce some output and want to write it back to a data store. And for the simplest iteration, it writes it back just to the database. And this is essentially what we do 2 or 3 times a day per customer for various steps in our pipeline. And this is where the the issue is. So if we scale this out for hundreds of workers, we have scalability issues. Because starting with the read, these joins are quite expensive, so the database, which is working behind the scenes, actually has to perform a lot of calculations. The CPU load is extremely high, and the network is also, of course, limited, so the data throughput is somehow limited. We can maybe read with 30, 40, 50 workers concurrently, but at some point it just stops, unless we scale up our database, and this is costly. So this is the one side of things. On the other side, if we have 200 workers and every worker produces a result, how can I insert them concurrently? A lot of databases have something like a table log to manage their transactions, conflicts, and so on. So concurrent insert is a difficult problem for typical databases. And this is where we thought, okay, we need something which is cheaper, because these, so we are using a distributed in-memory database for this one, which is quite expensive. So we need something which is cheaper, scales better for read and for write, and putting everything together, we of course looked around what's out there, and one of the things which come up is the typical stupid, so to say, object store typical cloud providers provide. Think of the Azure Blob Store, S3 in Amazon, or the Google Cloud Storage. And in a nutshell, these cloud storages allow you to store binary data with a bit of metadata, and that's it. But these blob stores are extremely fast and extremely scalable when it comes to concurrent writes and reads. So there's some really nice baseline for what we try to achieve. And this is, of course, not a new idea. If you look around for things like Hadoop, Presto, and similar technologies, they also use object stores. So this is, so to say, a natural starting point. And this is where Kartothek starts. But before I talk too much about Kartothek, I want to give you a quick introduction about what Dask is all about, because for all of those who have never heard of Dask or about what is a computation graph, this is a very quick introduction. So Dask, according to its own documentation, is a flexible library for parallel computing in Python. In a nutshell, it re-implements the API of very common libraries like pandas, NumPy tools, and so on, and offers big data collections which are built inherently for parallelization. So what it does, it implements a collection, for example, like a data frame, which is not built to run on a single machine, but on multiple machines. So how does it do that? Essentially, it knows that my data is partitioned in a certain way, and if I want to calculate something, a group by a sum, whatever, I can map this complex analytical task on much, much smaller tasks which are dependent on each other. And this is essentially the task graph Dask builds for you. And you can use this task graph and let it run on a single machine, multi-threading, multi-processing, or you use Dask distributed, which allows you to scale this whole thing up on a Mesos Kubernetes cluster or whatever, and have really full distributed load. And you can interact with this data frame as if you look at the entire memory at once. So you can work with terabytes of data in theory, although you only have very, very small commodity hardware virtual machines. What this looks like, for example, here, this would be a task graph, a very simple one. On the left-hand side, you can see how one would build up a graph from single computations, and in the end, you get a task graph. And what Dask can do now, start at the bottom with every single task and work its way through there until you receive your final result. If you look at a more complicated example in real time, this is what things might look like. So you build up a very complicated graph, which might be a group by over data frame, a join between data frames, or something similar. Dask maps out which tasks need to talk to which tasks and schedules them accordingly. And this is all the magic Dask does behind the scenes for you, and the API is usually supposedly exactly as easy as you would be working with a pandas data frame. So with that in mind, so we have these task graphs, and based on these task graphs, what can we do with it? we built Kartothek, which is a consistent table library management, management library in Python. So in a nutshell, if we very brief look at what this will look like, so we don't have SQL. We work in Python, and this is about as complicated as it can get because I'm using the full barrage of features we have. So on the left-hand side, you can see, okay, I'm reading a data frame. You provide a name, a store, maybe some columns you want to retrieve, and predicates. Predicates, think of them as a where clause, and that's it. Then you have your Dask data frame, you perform some calculations on it, some data processing, and in the end you store it. The storage function looks a little bit more complicated, but what's behind the scenes there, I will show you in a second, because that's the power of Kartothek. But the API is essentially that, you read and write stuff, and this is what Kartothek is about. At the very core of Kartothek, it started with a storage specification. So the idea, okay, I have a distributed data frame. I have many, many partitions, and I need to map this onto a physical file system, or not even a file system, but rather a blob store, which doesn't have even the notion of hierarchical data. So plain storages. One downside of these storages, of these blob storages, is that they cannot very efficiently list their content. So it is actually a scaling problem that if you have about a few 100,000 files in a blob store to retrieve all of your files. So this is also a scaling problem for these blob storage. So what Kartothek does is it tracks its state in a metadata file. So we have essentially, to simplify it, we have a single file, and this file contains a list of all partitions belonging to the dataset. And based on that very simple notion, everything else is built around it. We have indices, we have multi-table support, and whatever there is in there. I will show you a bit of how this works in a second. But the core idea of Kartothek is to track your files explicitly, because this way you have essentially you have to do only once, you have to only read once your metadata file, and then you know what everything is. Then you can plan your query, then you can plan your data retrieval path without looking too much into the store ahead. Because if you think about the performance for these data sets, there are two ground rules, so to say. The first one is don't touch any file. So if you don't touch any file, that's extremely fast. So if you read something which isn't there, don't look at the data. Or if you want to read a subset of your data, don't look at all of these files. If you have a few 100,000 files, this is very inefficient if you have to look at every single one, especially if the read goes over the network. The second thing for performance is, if you actually have to look, don't read the file, or at least not entirely. And these two concepts is essentially what performance is built around, and Kartothek is there to help you out to achieve these principles. So the first one, don't touch any files. How is this done? What Kartothek does, or what Kartothek offers as a feature, is that we have partition level indices. So if you build a data set, you can essentially remember all of the unique values of a column and remember in which file this data lies. So based on this, if I, for example, select value A of a given column, I know I only have to read five files instead of 5,000. So this is the first very basic but very powerful concept of how to shrink your data access. This is called partition pruning, and this is possible for us in essentially a constant amount of remote calls, because we have to read the metadata file, the registry, so to say. We have to read the indices, and based on this, we know everything we need to know about how we plan our data access. The second thing is, don't read everything at once. This is one of the core ideas of the Parquet file specification. So Uwe talked already about Parquet, and I will give you a very, very brief introduction about what Parquet is all about, because there's, at least to my understanding, one very important feature one should be aware of, which is called predicate pushdown. And how this works is essentially that Parquet splits your data into several chunks. So a very simplified view of such a data storage file can be seen on the right-hand side, where we store essentially chunks of every column in a certain order. And by this, we can calculate certain statistics which are stored at the bottom of the file. So if I want to read only a subset of the data, I look up where this subset of the data is living in. And then I only read maybe half of the file or maybe only 5%. This, together with the extremely well encoding and compression things the Parquet thing has to offer, which boils down or compresses your data about a factor 10 to 20, we reduce the network load sufficiently fast that these accesses are quite efficient. In reality, my pictures are obviously not really correct. If we look down below at how the specification looks like, it is very messy. But this is just because we store these statistics, we store type information, encoding, compression information, and so on and so forth. And as Uwe just said, nobody needs to know these gory details. Nobody needs to interact with Arrow or Parquet directly. But it helps to know a few things. So the important thing is that there are these statistics, and this helps us to be essentially extremely fast. How does this work? If we look at row group statistics, consider a very simple table. 2 columns, an integer column, a string column, and so on. And I define the chunk size, so I say my row groups should be split every 2 rows. This creates 2 row groups, and I calculate statistics, min-max. So I store the minimum value of a given column and the maximum value of a given column for every row group. There's one downside, though. If I, for example, want to read now in this example all data where A equals 2, my min-max statistics don't tell me too much. So I still have to access 2 row groups. So I have to read the entire file in this instance. This is where we need to sort the data. And all of a sudden, if I want to query A equals 2, I only access a single row group. So essentially, I can boil down my data access pattern to only a fraction of the actual file. And considering that no matter how fast network is, it is always a bottleneck, this is something extremely valuable. So with these 2 things in mind, we can look at what Kartothek does. It writes and reads data. So how does writing a Parquet dataset look like? And again, think in this scenario as every single table you can see here would be data on a Dask worker. So they are distributed. So everything works in parallel. And what I can do now, for instance, if I have 3 of these objects, I want to store it, then what Kartothek does, it takes your data and performs certain steps. One of the steps is, of course, the first one is parsing the stuff, but subsequently we calculate all these important statistics. We calculate, or we allow you to split the files. So there's one feature which is called partition on, which gives you a little bit control about how your physical partitioning looks like. Because as I said in the beginning, touching as few files as possible is key to performance. So when you write data set in this distributed fashion, you should be aware of how your data should look like physically. So the partition on gives you the possibility to split your data essentially on several files. So in this instance, I'm using partition on the column A. So every single input file is split according to its values in A and stored in a physical file, which you can access. Also, I'm calculating an index information on maybe the column B. And in this case, I then have 2 indices which I can use to query my data set. A primary index, which is on A, because I split the files. And the primary index means essentially for every file has only a single value of that column in it. So all rows of a given physical file has only one unique value. The secondary index is a little bit more messy. You can have multiple of these in a physical file, which is of course not beneficial, but the idea behind it, you can essentially calculate an index on every single column. So if you know, okay, I'm usually accessing my data using these 2 or 3 columns, build an index on it, and in the end, you maybe only need to look at a single file. And considering that if your data set is a terabyte large and you have a few 100,000 files, this is quite important for your performance. I told you before that Kartothek, so this is nothing very special, even Dask can do this, especially partition on, this is a standard feature of Dask. But what Kartothek offers you is the indexing, and it gives you a little bit more control about how the files look like. So for instance, if you look at the bottom 3 files, all have the same value. And this is what Kartothek offers you, that essentially it allows you to combine these into a single file. So it gives you a little bit control about how your storage layout looks like. And you may benefit from this later on when reading the data. So you can engineer your data set such that the application which follows up has essentially perfect performance. But the whole thing is hidden behind the scenes. So reading the thing, you don't need to be aware of the physical partitioning, because this is what Kartothek does for you. It tracks this whole thing and resolves the indices and so on and so forth when reading this. One very important thing at the very end of this write operation is the collector task here, which is named it's written there as collect, verify, and commit the data set. Because this is something which is rather special. Since we store references to all of our files, we can commit, we can perform an actually atomic commit where we set the state of our data set in stone. So even if your computations fail, if they are not idempotent, or if there is something wrong with it, some integrity checks fail, the commit fails, and this gives you data consistency, which is extremely important if you run in day-to-day production services. So this data set commit is one of the key ideas of this data tracking, and it performs a few steps. For once, it stores the table schema. The table schema is essentially a list of columns, a list of types, and what Kartothek does is it checks that everything you commit is actually consistent. So it doesn't allow you to store partitions of different types or of different columns, because in the end, if you read it, that wouldn't make any sense. And it performs these commits if and only if this consistency is actually guaranteed. And this is quite nice, because this allows you also to modify this data set. You can append data, you can remove it, you can replace data. So you can, and this is something which is not by default when you're using, for instance, Dask. You cannot simply grow it, because if your computations fail, you read the data and you're not sure, okay, what's actually true here. By tracking everything explicitly, you always know the data you're looking at is consistent. The type stability itself is also a rather big deal. If you've been working with pandas, as I assume you have, there are certain issues. So for instance, in this example here, I'm showing you 2 partitions. The one is a Boolean, true, false, true. The other one is a none. So if you would, in your distributed application, try to store these 2 partitions, this would be rejected. The commit would fail. Why? Because if I load it, something weird is happening. All of a sudden, I don't have any bool columns anymore. I have object columns. And this has several implications. First of all, it is unstable. Sometimes different types behave differently. That's not nice. Another issue is your performance degradation is massive. So if you have an integer column, for example, or a Boolean in this case, and all of a sudden you're using the plain object columns, this is performance degradation of maybe a factor of 1,000 if you want to do something like group by. So data consistency is extremely important, especially if you run in your computations in a machine learning stack, your custom code. You cannot rely, okay, on a Dask does a group by sum, it knows what it's doing. But if you run your own custom code and the output is something which you store, this data consistency is extremely important. Especially once you go down to predicate pushdown, when you need to compare values on this physical layer, this type check is extremely important, because how do you compare a string to an integer and so on and so forth. So by having everything consistently wrapped up, this gives you a little bit of breathing room. The table schema, this is something Uwe already mentioned, is something we use arrow types for. So we have, in the end, we support all the arrow tables, and we store this whole thing in Parquet and read it out as an arrow table, which gives us also the opportunity to interface with other languages. We, for example, are using some C++ code which accesses this data. And by using Arrow, we can essentially read the Parquet file, transform it, and pass it directly to C++ without any copy operation. And this is extremely, so we've seen performance increases of multiple factors just because of things like these. There's one downside to all of this. If you use two pandas, these types don't actually map one-to-one, but this is fairly straightforward, and I won't go through this table just for you to know. There is some mapping, and it's sometimes a little bit different than you would expect. For instance, the date column, there is no date in pandas, but yeah, well, that's the way it is. There are some downsides. As I said, one of the very, very useful features which you can use is update stuff. So this is an example code on how you could update a data set. So consider you have a database where you store customer data, and you have a Parquet table which is used by your machine learning application. So at some point you need to synchronize this, and you don't want to download everything at once or every day again. What you only want to do is maybe download just a chunk for today or this week or last week or whatever. So appending to a given data set is actually quite important, and this is the code how you could do this. So you write a simple function which would be something like download data from database. And as you can see, I'm using TurboDBC, which is a quite efficient way to load the data, which also uses Arrow underneath. So this is fast, and I simply loop over the dates I want to download and create Dask delayed objects. And after that, I pass everything to Kartothek, and the data set grows continuously. And if anything fails, if your data becomes inconsistent, if some type changes, if columns change, the commit will reject this, you will know, and no silent errors sneak into your system. So what about reading the whole thing? Because storing it, writing it is only the one side. At the end, you need to read it because your machine learning application or whatever your application is wants to consume the whole thing. And as I said, we don't have SQL. There are reasons for that, but you can essentially query a data set like this. At the upper left corner, you can see the read table function, where we essentially provide columns and a list of predicates. So think of the predicates as a where clause. In this case, I would like to retrieve A equals 2 and B equals B, and C should be smaller than 0.3. And as I've shown you before, okay, in this particular instance, we have indices. So my indices, without touching any file, tells me already that to read this query, I only need to look at these two files on the lower left side, because both indices exclude certain files, and by this I can essentially create only 2 jobs instead of 2,000, which read the data. The next level would be that I actually read the data, and in that case the predicate pushdown comes into work, because for the one partition I ask for, okay, give me something with B equals 2, with B equals B and C smaller than 0.3, and the Parquet file tells me, you know, there is not a single value where C is actually smaller than 0.3, so don't load any data. But Kartothek manages this, that there's still, so you get an empty data frame essentially. This is important because if you want to combine these partitions in the end, a stable type system is, again, very important. On the other side, you retrieve a subset of the data because I'm using chunking. I'm using chunk Parquet files. So I actually retrieve only 2 of 3 columns. And in the end, I perform a final filter, and my end result is essentially exactly what I queried. And this is something, if you cut your data set from the physical partitions properly and know what the application downstream will actually query, this allows you to have sub-second response times for small queries, even for really, really large data sets, so about terabyte scale, depending on how you slice and dice your data. And that's essentially it. We can read and we can write data, and that's everything we want to do. And if we summarize this, Kartothek does nothing else than it stores flat data as a Parquet data set. But, and this is very important, this is consistent. You don't commit any data which is not supposed to be there. You don't commit data from a failed run. You only commit what should be there. We can read very fast without any locking mechanism. We're using the blob store, we're using S3, whatever you wish to choose, and this gives you high concurrency. So you could think about, I don't know, shuffling 200 gigabytes in 5 or 10 minutes over the network. This is what a blob store can do for you. But the whole query planning, if you want to only select something very special, is extremely fast because we actually don't need to talk to the store that much. And the most important thing is, this is built in Python for Python. We have the Dask API, we're using the Dask API, we are very familiar with pandas, and the interface this exposes is essentially a seamless integration into the ecosystem. So if you have, or you are a data scientist who is working with scikit-learn, pandas, NumPy, and everything else, this is exactly the interface he expects. Not something like a PySpark data frame or some weird other data format, but pandas is exactly what he expects. So, as I said, this is an open source project. We've been working on this whole thing for about 2 years. We open sourced it only maybe 2 months ago, so this is why there is not much going on yet. But we released this as version 3.0, which should give you an impression about the stability, because we are actually using this in production and we will continue to improve it. So if you feel like this might not be stable enough, well, I might agree that certain things might change, but we are using it in production and we have a very strong interest in keeping it alive and stable and working. So this should not hold you. And of course, contributions are welcome. So if you are familiar with Pandas, Arrow, Parquet, Dask, Spark, so the whole thing is built in a way that we can essentially extend it to other scheduling engines. This was one of the core ideas, because in fact, when we started this whole thing, we didn't have Dask in our company, but something else entirely. So the whole thing is built with this modularization in mind. If you prefer some other file format than Parquet, which I would not recommend, but you can also use that. Yeah, CSV, okay, we actually support CSV. So everybody needs to support CSV. But yeah, that's it. CSV and Parquet so far, but if you like to use Arrow or something like this, there's also an interface where you can just plug this in. So this brings me already to the end of my talk. Last but not least, as I said, I'm working at Blue Yonder. I'm doing stuff like this. I'm working open source, data engineering. I'm working with machine learning experts all day. We are looking for data scientists, data engineers, front-end engineers, site reliability engineers, and much more, which I couldn't fit onto the slide. So essentially, if you have expertise in anything, talk to us. Write an email or approach us on Twitter. We have currently 2 GitHub accounts, because there's one for JDA, which acquired us, and one for Blue Yonder. We will merge this in the future, but so far, look at these. One of the things you can find at the Blue Yonder site, for instance, is TS-Fresh for machine learning time series analyzation, or TurboDBC, which you talked about earlier. So, yeah. That's it for me. Are there any questions? Yep.
So I still want to get a better understanding of the play with Dask and
yep.
What's it called again? Sorry, I forgot the name of Kartothek. Yeah.
Yeah.
There was a slide. Yeah, this one. I first thought that Kartothek is running on its own, but if I see the last block, how is it combining again? I lost it at some point.
So we offer several interfaces. So Dask, for instance, has several collections like the data frame, a bag, or some more low-level objects like the delayed object. This example uses the delayed, Dask delayed. This is essentially what the for loop is doing. And the delayed object allows you to essentially build your task graph on your own. A different interface would be that if you manipulate some data frame because you're running some fancy large-scale machine learning or so on, you can use a different function and just throw your Dask data frame in there, and the data frame is then translated into the physical partitioning. So there are different interfaces for different collections. Yeah. And Dask, Kartothek itself is not running on anything. It essentially just assembles the logic which we need to do to have this dataset state in the end. And the execution itself is handled by Dask. This is also the reason why you can, for instance, write a PySpark implementation, because the logic of the individual tasks is Kartothek. So, for instance, how to calculate an index, how to combine these, how to commit a data set. This is logic we provide, and we use Dask only to plug these together to allow the distributed execution. And you could do the same thing for Spark or for something else entirely.
Because what I took away you made Kartothek to have the consistency.
Yes.
This is the thing that you were missing.
Yes.
And maybe one more reason, because there was, you said about the control of the chunks.
Yeah, this is one example, yes, where we can essentially have better control about what's going on by fusing these partitions or by splitting them up, building indices and things like these. Essentially, we have better control about the performance which is happening. Yes, so performance should be better simply because we don't have to look up all the files. If you call, for instance, Dask read Parquet, which is also supported for S3, for example, it first iterates over all blobs, which is painfully slow, to be honest. And only after that, it assembles, okay, my data set looks like this. And then it starts planning. And for Kartothek, it knows this from the very beginning. So you have lower latency for query planning, and I would dare saying that even the read speeds and so on are better. I wanted to write the benchmark, of course, because this is interesting. Then I realized that Dask doesn't offer an interface for the Azure Blob Store, and this is where all our data lies. So this is something I will prepare for my next talk, that I somehow put our data on S3, but this is, of course, something we cannot just move our customer data somewhere else. So this is, I will figure out a solution to that issue, because, of course, performance benchmarks are key in these scenarios. But trust me, on that regard, for instance, alone parsing, listing a blob, if you have 100,000 or 200,000 keys, this may take minutes, 10, 20 minutes, only listing. And this is only when Dask can start, okay, now I know what kind of data I'm looking at. And okay, most of what I read right now I don't need, because I have some kind of indices, and only then it starts reading stuff. So the latency, the query planning, the scheduling is much, much slower if you use these, so to say, on-the-fly parsings, which are done by Dask, Spark, Hive, Presto, and so on and so forth. So, yeah.
Right. So, specific question varies in that direction. If Spark and Hive meta store, then what's the improvement of that?
Yeah. So a Hive meta store is essentially this idea of tracking the state of these Parquet files in a place which has strong or fast read access is essentially the idea of the meta store. So what Kartothek does, it puts this, so there's no need for this meta store.
You have a meta store, it's just JSON file.
Essentially, yes. Yes.
So then I guess I'm wondering, so if you want to please me not to use Hive meta store, but Kartothek instead, I guess I'm still trying to want to use Kartothek, and then I would rather stick with Hive or Spark and meta store.
So the important point to take away for me with Kartothek is the Python interface. Because if you use Hive, yeah, that's so there. Hive is something special. Spark, for instance, could do the same. So it gives you more or less a pandas-like API, and you can retrieve a pandas data frame, but you lose the consistency. Spark itself also doesn't offer you consistency. Spark itself also has the issue of scalability of the blob store. It also needs to list every single file. So you need something like a meta store. And yes, we are using a JSON file as our meta store.
What do you mean by consistency in this case? That we lose consistency within the use.
So consider you have a batch job which consists of 1,000 jobs. And you want to use this data only if all of your jobs are successful. Or you want to use only the data of successful jobs because a job might retry for some reason and writes the same thing twice. So all of these instances might introduce anomalies because you might have duplicate data, you might have missing data, you might have inconsistent data types, and all of these things should be not an issue if you use explicit state tracking.
And if one uses Spark, then you have this inconsistency.
Yes, potentially, yes.
Results in worse performance or results that some wrong results?
Well, it depends on the error which is actually there. If you're missing data, you're simply missing data, so your analysis is incorrect. If you write duplicate data, you have duplicates in there. If you have inconsistent types, frankly, I don't know what Spark would do, or what would happen, probably crash at some point or upcast the data, which is also something you wouldn't want it to do. So these are various edge cases which are introduced by this lazy or by not tracking the state explicitly. And things like, this example, the update example, is something I'm not aware of that you could map with simply Spark or simply Dask, because how do you mutate the data set, and how do you know that this mutation was successful if you do not track the state explicitly? So if you remove data, if you add data, and something happens in between, for instance, you removed half of it, but you append only a single file, but you intend to append a lot more. So you are in an inconsistent state in between. So this is something, if you want to update stuff or modify this data set, insert new partitions, remove one, this consistency and the state tracking is actually key. So since these questions came up, we are not the only ones in town, because this idea is also not very unique. But we started before this got open sourced. So this Apache Incubating Iceberg is something which was released about a year ago by Netflix. And the idea is essentially the very same. They have a storage specification which is a little bit more sophisticated than what we offer. But essentially the idea is the same, that you store and track the state explicitly because of various reasons, of consistency, of constant query planning time to reduce latency. And this is a tool which is very well integrated into the Java ecosystem. So if you want to use Hive, this is where what you need to do. This offers you same consistencies than Kartothek does in the Python world, but for the Java world, and exposes this and offers this for things like Presto, Hive, Spark as well. And one of the things we would like to do as Kartothek is move or evolve our own specification to be in accordance to the Iceberg specification, because this would also allow us to pass around our data more freely between different ecosystems. But this is down the road, and there's currently not an implementation. All right, so I think I'm over time. So